Picture this: a moment frozen in time. A burst of light so colossal it birthed everything we know. The Big Bang didn't just create the universe, it left behind a ghostly fingerprint, a whisper of heat and radiation that still lingers in the void. This is the cosmic microwave background, the oldest light in existence, and it's not just a relic, it's a living, breathing clue to how our cosmos grew from a searing hot singularity into the vast, glittering expanse we see today. But here's the strangest part: that ancient energy isn't just a memory. It's still shaping the universe right now, bending galaxies, sculpting the voids between stars, and even tugging at the very fabric of space itself. Think about the last time you stood outside on a clear night, staring up at the stars. Every one of those pinpricks of light, every swirling galaxy, even the empty blackness between them, it's all connected by echoes of that primordial explosion. The cosmic microwave background is like a cosmic blueprint, a map of the universe's infancy that holds the answers to questions we're only beginning to ask. Why does the universe look the way it does? How did something as delicate as a planet or a person come to exist? And what invisible forces are still at work, pushing and pulling the cosmos in ways we can't yet fully grasp? This isn't just a story about the past. It's about the present and the future, too. That faint afterglow of the Big Bang is still influencing everything, from the way galaxies spin to the mysterious dark energy that's tearing the universe apart at an ever-increasing speed. It's a reminder that we're not just observers of the cosmos, we're part of its unfolding story. So let's trace those echoes back to their source, unravel the secrets they carry, and discover how the universe's first breath still shapes our reality today. The journey starts here, in the faintest whisper of heat left over from the dawn of time. To truly grasp how the universe evolved from that initial burst of energy, we need to rewind the clock, back to when everything we know was compressed into a space smaller than a single atom. The Big Bang wasn't an explosion flinging matter outward like shrapnel. Instead, imagine space itself stretching, inflating faster than light in those first fleeting instants. Picture a cosmic cauldron, hotter than the core of any star, where particles and energy collided so violently that matter and light were trapped in a swirling, opaque soup. For hundreds of thousands of years, the universe was too dense for light to travel freely, until finally, expansion cooled things enough for atoms to form. That moment of liberation, when light broke free, left an indelible mark. The cosmic microwave background is that light, now stretched and faded by billions of years of cosmic expansion. It's not just a snapshot of the universe at 380,000 years old. It's a treasure map. Tiny fluctuations in its temperature, no bigger than 1 part in 100,000, reveal where matter clumped together slightly more densely. Those minuscule irregularities became the seeds of everything: galaxies, stars, even the vast cosmic web threading the void. But here's what's astonishing. The CMB isn't just a fossil, it's still interacting with the universe today. As this ancient light travels through space, it gets subtly distorted by galaxy clusters and dark matter, bending like a mirage in a desert. Scientists study these distortions like detectives examining fingerprints, uncovering hidden structures in the cosmos and the patterns in that glow. They're proof of quantum fluctuations from the universe's first trillionth of a second, random ripples magnified to cosmic scales during inflation. This is why the cosmic microwave background isn't just a relic. It's a bridge between the universe's fiery birth and the delicate structures that allowed life to emerge. Without those faint whispers of heat, galaxies might never have formed, and the night sky would be nothing but endless, empty black. So when you look up at the stars, remember, you're seeing the legacy of those primordial ripples, written in light that's been traveling since the dawn of time. Sometimes the greatest discoveries happen by accident, like when two radio astronomers in New Jersey spent months chasing a mysterious hiss they couldn't eliminate. Arno Penzias and Robert Wilson were just trying to calibrate a sensitive horn antenna in 1965, but no matter how carefully they adjusted it, that stubborn static remained. They even scrubbed out pigeon nests and cleaned droppings from the equipment, convinced the noise had to be interference, but the truth was far more extraordinary. What they'd found wasn't a technical glitch, it was the faint afterglow of creation itself, the cosmic microwave background radiation predicted by Big Bang theorists years earlier. This accidental breakthrough changed everything. That persistent hiss matched precisely what scientists had calculated. The cooled remnants of the universe's first light, stretched over billions of years from visible wavelengths into microwaves. For the first time, we had concrete evidence that the cosmos began as a searing hot fireball, not an eternal, unchanging void as some had believed. Penzias and Wilson's discovery earned them a Nobel Prize, but more importantly, it handed cosmologists a time machine. That static was a baby picture of the universe at just 380,000 years old, capturing the moment atoms formed and light finally broke free from the primordial plasma. What makes this snapshot so valuable are the tiny imperfections hidden within it. At first glance, the CMB appears almost perfectly uniform, a thermal blanket glowing at a frigid 2.7 degrees above absolute zero. But look closer and you'll spot minuscule temperature variations, fluctuations no larger than 1 part in 100,000. These faint ripples are cosmic gold. They mark regions where matter was ever so slightly denser, gravitational seeds that would eventually grow into galaxies and galaxy clusters over billions of years. It's like finding the faint brushstrokes on a canvas that later became the Mona Lisa, the universe's first rough sketch of everything we see today. Modern satellites like COBE, WMAP, and Planck have mapped these fluctuations in stunning detail, revealing patterns that tell us exactly how much ordinary matter, and dark energy fill the cosmos. The CMB's fingerprint even holds clues about inflation, that mind-bending moment when the universe expanded exponentially in the first fraction of a second. Without those primordial ripples, gravity would have had nothing to work with, leaving space an empty, structureless void. So the next time you hear static on an old radio, remember, it might just be the faintest echo of the universe whispering its origin story. That first light breaking free was more than just a cosmic dawn. It was the universe's first breath, a moment when the fog of creation finally cleared. Imagine being there, floating in that newborn cosmos, watching as photons, particles of light, escaped their plasma prison after hundreds of thousands of years. Suddenly, space became transparent, glowing like an ember cooling from white-hot to red. But what's truly remarkable is how that light didn't just vanish into the void. It carried with it a secret, a hidden pattern etched into its very fabric. Those faint temperature variations in the cosmic microwave background, those tiny ripples of hotter and cooler spots, might seem insignificant at first glance. Yet they're the universe's original building instructions. Think of them like tiny hills and valleys in an otherwise smooth landscape. Over billions of years, gravity went to work on those subtle irregularities, tugging ever so slightly harder on the denser regions. Matter began to clump around these cosmic seeds, snowballing into vast clouds of gas, then stars, then galaxies. The grand tapestry of the cosmos, threaded with galaxy clusters, superclusters, and the sprawling cosmic web, all trace back to those minute fluctuations in the CMB. Here's where it gets even more fascinating. The CMB doesn't just show us where matter was, it reveals how the universe grew. By studying the precise size and distribution of those ripples, scientists can measure the universe's expansion rate, its composition, even the influence of dark matter. Those patterns are like cosmic barcodes, encoding everything from the total amount of matter in existence to the way dark energy is stretching space itself. And the implications are staggering. Without those primordial density variations, the universe might have remained a featureless sea of particles. No galaxies, no stars, no planets, just an endless, uniform haze. The fact that we exist at all is tied to those faint whispers of imbalance in the early cosmos. So when we map the CMB today, we're not just studying ancient history. We're reading the blueprint of reality itself, a blueprint that's still guiding the evolution of everything we see in the night sky. Those tiny temperature differences in the cosmic microwave background, no bigger than 100,000th of a degree, might seem insignificant. But they're the universe's original architects, the hidden blueprint for everything that followed. Picture a vast ocean where some areas have just a few more water molecules than others. Over time, gravity acts like a cosmic magnet, pulling those slightly denser patches together, drawing in even more matter. What began as microscopic ripples in the fabric of space-time became the foundation for galaxies, stars, and ultimately us. Supercomputer simulations bring this process to life, showing how those initial density fluctuations snowballed over billions of years. Dark matter, an invisible, mysterious substance that outweighs regular matter 5-to-1, played a crucial role, forming an invisible scaffold that ordinary matter could cling to. Without those subtle variations, gravity would have had nothing to work with, leaving the universe a cold, empty expanse. Instead, we see a cosmos teeming with structure, from the delicate spirals of galaxies to the sprawling filaments of the cosmic web. The precision of those early fluctuations is staggering. If they'd been even slightly stronger, matter would have collapsed into black holes long before stars could form. Too weak, and galaxies might never have taken shape. It's as if the universe walked a tightrope, balancing its own ingredients with exquisite care. And the echoes of that balancing act are still visible today, etched into the distribution of galaxies across the sky. This isn't just theoretical, we can see the evidence with our own eyes. Maps of the modern universe reveal vast voids and dense clusters, mirroring the patterns in the CMB with uncanny accuracy. It's proof that the seeds planted in the universe's first moments grew into the cosmic landscape we inhabit. And it raises an even deeper question: what caused those fluctuations in the first place? The answer might lie in quantum mechanics, where particles flicker in and out of existence, leaving behind traces that inflation stretched to cosmic proportions. But the story doesn't end there. While ordinary matter clumped together under gravity's pull, dark matter was weaving its own invisible web, shaping the universe in ways we're only beginning to understand. Dark matter is the universe's silent partner, an invisible force shaping everything we see while remaining utterly elusive. It doesn't emit light, absorb it, or interact with ordinary matter in any way except through gravity. Yet its gravitational grip is so powerful that it dictates the motion of galaxies and the very structure of the cosmos. Think of it like the wind. You can't see it, but you can see its effects in the bending of trees or the ripple of waves. In the same way, dark matter's presence is revealed by the way galaxies spin faster than they should, how light bends around galaxy clusters, and how those primordial density fluctuations in the CMB grew into the vast cosmic web we observe today. Without dark matter, the universe as we know it wouldn't exist. Ordinary matter, the stuff of stars, planets, and people, makes up less than 5% of the cosmos. Dark matter outweighs it by a factor of 5, meaning it's the dominant architect of cosmic structure. When the universe was young, dark matter's gravity acted like a scaffold, pulling ordinary matter into its invisible folds. Those slight overdensities in the CMB, dark matter amplified them, accelerating the collapse of gas and dust into galaxies. Simulations show that without dark matter's gravitational boost, galaxies would have taken far longer to form, and many might never have come together at all. The James Webb Space Telescope is now peering back to the universe's infancy, searching for the faintest, earliest galaxies to understand how dark matter guided their birth. Already, it's revealing galaxies that are too massive, too mature, to exist so soon after the Big Bang, hinting that dark matter's role was even more crucial than we thought. But for all its influence, dark matter remains maddeningly mysterious. Is it a particle, a cosmic fossil from the first moments of time, or something even stranger? What's certain is that dark matter and the CMB are intertwined in a cosmic dance. The patterns in that ancient light map the distribution of both ordinary and dark matter, showing us where gravity's invisible hand was strongest. And as we unravel these clues, we're not just solving a puzzle, we're rewriting the story of how the universe built itself. Yet there's another player in this story, one that defies gravity itself, dark energy. Just as dark matter pulls the cosmos together, dark energy is tearing it apart. If dark matter is the unseen hand sculpting the universe's structure, dark energy is the shadowy force ripping it apart. In the late 1990s, two teams of astronomers made a discovery so shocking it upended decades of cosmic assumptions. By observing distant supernova, they found that the universe wasn't just expanding, it was accelerating, as if some invisible repulsive force was pushing space itself apart faster and faster. This wasn't just unexpected, it defied everything we thought we knew about gravity's role in cosmic evolution. The culprit, a mysterious phenomenon dubbed dark energy, now believed to make up nearly 70% of the universe's total energy. Here's why this changes everything. For most of the 20th century, scientists assumed the universe's expansion was slowing down, with gravity gradually pulling galaxies back together in a cosmic tug of war. The Big Bang might have set everything in motion, but gravity was supposed to act like a brake, eventually leading to a big crunch, or at least a gradual coasting. Dark energy flipped that script entirely. Instead of slowing, the expansion is speeding up and has been for billions of years. Space itself is stretching, not just between galaxies but within them, creating a future where distant galaxies will vanish from view as their light can no longer outpace the expansion. The cosmic microwave background holds vital clues about this enigmatic force. By precisely measuring the CMB's temperature fluctuations, scientists can calculate how much dark energy exists and how it's influenced the universe's growth. Those faint ripples in the afterglow act like a cosmic speedometer, revealing how quickly space has expanded over time. The patterns suggest dark energy wasn't always dominant. In the universe's youth, gravity and dark matter ruled, allowing galaxies to form. But around 5 billion years ago, dark energy took over, and its repulsive push began winning the battle against gravity's pull. What makes dark energy even stranger is that it seems to be a property of empty space itself. Unlike matter or radiation, its density doesn't dilute as the universe expands. More space means more dark energy, creating a feedback loop where expansion begets faster expansion. Some theories suggest it's related to Einstein's cosmological constant, a sort of energy of the void, while others propose entirely new physics. But one thing is certain, without dark energy, the universe would look radically different. Galaxies would cluster more tightly, and the vast cosmic voids we see today wouldn't exist. The interplay between dark energy, dark matter, and the primordial energy imprinted in the CMB is what shapes our cosmos. Dark matter builds the scaffolding, ordinary matter forms the stars and planets, and dark energy dictates the ultimate fate of it all. Together, they weave a story that began with the Big Bang's first flicker of light and continues to unfold in ways we're only beginning to understand. And the key to deciphering this cosmic puzzle, it's written in the oldest light there is, the whispers of heat left over from the universe's fiery birth. The cosmic microwave background is more than just an ancient glow. It's the universe's most precise measuring tape, those subtle temperature variations, frozen in time when the cosmos was just 380,000 years old, let scientists calculate fundamental properties of reality itself. Imagine stretching a ruler across 14 billion light-years. That's essentially what researchers do when analyzing the CMB's fluctuations. The distance between those hot and cold spots reveals the universe's geometry, acting like surveyor's marks on a cosmic blueprint. Planck, the European Space Agency's flagship mission, mapped these variations with unprecedented precision, confirming something extraordinary. Our universe is flat too, within a razor-thin margin, less than 0.4% deviation from perfect Euclidean geometry. This flatness isn't just a geometric curiosity, it's a direct consequence of the universe's total energy density. Too much matter and space would curve inward like a sphere. Too little and it would sag outward like a saddle. The CMB shows we're in the Goldilocks zone where parallel lines never meet, proving the cosmos contains just enough matter and energy to balance on this knife edge. But the real bombshell came when Planck's data revealed the cosmic recipe. Ordinary matter, the atoms in stars, planets, and our bodies, accounts for a mere 5% of the universe's total content. 27% is dark matter, its gravitational fingerprints visible in how galaxies rotate and cluster. The remaining 68% dark energy, that mysterious force accelerating the universe's expansion. These proportions aren't arbitrary. They dictate everything from how quickly galaxies form to whether the cosmos will eventually tear itself apart. Yet the CMB keeps throwing curveballs. One baffling anomaly, nicknamed the axis of evil, shows unexpected alignments in the temperature fluctuations that seem to defy standard cosmology. Some regions of the sky appear slightly warmer than they should be, while others are cooler, as if the universe has a preferred direction, something Einstein's theories say shouldn't happen. Whether this is a statistical fluke, an undiscovered systematic error, or a crack in our cosmological models remains hotly debated. These measurements are more than academic exercises. They're refining our understanding of cosmic evolution, forcing us to question whether we've missed something fundamental. The CMB's precision data has already ruled out entire classes of theoretical models, narrowing down the possibilities for dark matter and dark energy. And as we push these observations to even finer scales, we might uncover clues about what came before the Big Bang itself. Now, to grasp how these primordial fluctuations originated, we need to rewind further, to the universe's first trillionth of a second. This is where inflationary theory enters the stage, a concept so radical it reshaped our entire view of cosmic beginnings. Inflation proposes that the universe underwent a faster-than-light growth spurt, magnifying quantum ripples into the density variations we see imprinted on the CMB. Without this explosive expansion, those tiny fluctuations could never have seeded the galaxies we see today. So what powered this brief but monumental event? The answer lies in primordial energy itself, a field so potent it could stretch space-time like taffy in the blink of an eye. The universe's first moments were anything but calm. In a fraction of a second so small it defies imagination, less than a trillionth of a trillionth of a trillionth of a second, space itself erupted in a growth spurt so violent it makes the Big Bang look tame. This is inflation, the theory that the cosmos expanded faster than light in its infancy, stretching a speck of space smaller than a proton to the size of a grapefruit almost instantly. And it wasn't just space that got stretched. Tiny quantum fluctuations, random ripples in the fabric of reality, were blown up to cosmic proportions, becoming the seeds for every galaxy, star, and planet we see today. Why does this matter for the cosmic microwave background? Without inflation, the CMB's near-perfect uniformity would be impossible. Picture two opposite sides of the sky, billions of light-years apart. They've never been close enough to exchange heat or information, yet their temperatures match almost exactly, down to a few millionths of a degree. Inflation solves this mystery by proposing that these regions were once neighbors, crammed together in that primordial speck before being flung apart. The same quantum ripples that became galaxies also left their mark on the CMB's temperature patterns, like fingerprints pressed into cooling wax. But inflation didn't just smooth out the universe, it also imprinted a unique signature, primordial gravitational waves. These aren't the ripples from colliding black holes we detect today. These would be waves from space itself vibrating as it expanded, a relic so faint it's buried in the CMB's polarization patterns. Finding them would be like uncovering a recording of the universe's first heartbeat. Projects like the upcoming Light-Bird satellite are hunting for this signal, and if they succeed, it would be the smoking gun for inflation, proving that the cosmos really did undergo this unimaginable stretch. Yet for all its elegance, inflation isn't the only game in town. Some theorists argue it's too flexible, capable of explaining almost any observation after the fact. Alternatives like bouncing cosmologies suggest the Big Bang wasn't a true beginning but a rebound from a previous collapse, while string theory landscapes propose endless universes bubbling up in a multiverse. What makes inflation the leading contender is its ability to explain the CMB's fine details, but the debate is far from over. The next chapter in cosmology might rewrite the story entirely, revealing that our universe's birth was even stranger than we dared imagine. Inflation may be the leading explanation for the universe's explosive beginnings, but it's not the only idea on the table. Some cosmologists argue that the Big Bang wasn't a true beginning at all, just the latest chapter in an endless cycle of cosmic rebirth. Picture a universe that doesn't start with a bang but with a bounce, like a ball rebounding after hitting the ground. This is the core of bouncing cosmology, a theory proposing that our expanding cosmos was preceded by a collapse, a previous universe contracting under gravity until it reached a point so dense and hot that it bounced outward, birthing the reality we know today. What makes these alternatives compelling is how they tackle the same puzzles inflation solves, like the CMB's eerie uniformity, without requiring a faster-than-light growth spurt. In cyclic models, the universe's smoothness comes from a previous epoch's natural stretching, not an abrupt inflationary expansion. And instead of quantum fluctuations seeding galaxies, density variations might arise from collisions between higher dimensional branes, hypothetical structures predicted by string theory. These ideas are speculative, but they're not science fiction. They're grounded in rigorous math, offering testable predictions that could one day challenge inflation's dominance. The hunt for evidence is already underway. While inflation's fingerprints should include primordial gravitational waves, bouncing cosmologies predict a different signal, a telltale twist in the CMB's polarization patterns. Experiments like the Simons Observatory and future space missions are scanning for these subtle distortions, which could reveal whether the universe has a cyclical history. There's even a chance that anomalies in the CMB's large-scale structure, like the mysterious axis of evil, might hint at a pre-Big Bang phase, yet these theories face hurdles. Explaining how a collapsing universe rebounds without violating known physics is no small feat, and cyclic models often rely on unproven concepts like extra dimensions. Inflation, for all its mysteries, fits snugly with quantum field theory and general relativity. Still, the debate is healthy. It reminds us that cosmology is far from settled. The CMB isn't just a relic, it's a cosmic courtroom where competing theories present their cases, and we're the jury weighing evidence that's billions of years old. What's at stake isn't just academic. If the universe cycles endlessly, then time itself might be infinite, with no true beginning or end. Stars, galaxies, and life could arise over and over, each iteration subtly different from the last. Or perhaps our cosmos is one bubble in a frothing multiverse, where other universes obey entirely different laws. These possibilities stretch the imagination, but they're rooted in the same question: how did the primordial energy we see imprinted in the CMB come to be? The answer might rewrite not just the story of our universe's birth, but the nature of reality itself. As we peer deeper into the CMB's whispers, we're not just studying the past, we're probing the boundaries of physics. Whether inflation, bouncing cosmologies, or something even stranger wins out, one thing is certain: the universe's first moments were far more complex than we once imagined. And the next breakthrough could come from a subtle anomaly in ancient light, a clue hidden in plain sight since the dawn of time. For nearly 100 million years after the Big Bang, the universe was a vast, silent darkness, no stars, no galaxies, just a cooling sea of hydrogen and helium gas. Then, in pockets where matter had clumped ever so slightly denser, gravity finally gained the upper hand. Gas clouds collapsed under their own weight, compressing until the pressure and heat at their cores became unimaginable. In that instant, nuclear fusion ignited, and the first stars blazed to life, piercing the cosmic gloom like matchsticks struck in an endless void. These were no ordinary stars. Astronomers call them Population Roman III, the pioneers of starlight, forged from pristine hydrogen and helium with not a trace of heavier elements. Without metals to help them cool and fragment, they grew to staggering sizes, some hundreds of times more massive than our Sun. Their brilliance was equally extreme, burning ferociously at temperatures that would make today's stars seem dim by comparison. But such intensity came at a cost. These stellar giants lived fast and died young, exhausting their fuel in mere millions of years before exploding in titanic supernova that seeded the cosmos with the first heavy elements. The impact of these stars can't be overstated. Their ultraviolet radiation acted like a cosmic blowtorch, stripping electrons from surrounding hydrogen atoms in a process called reionization. This transformed the universe from an opaque fog into the transparent expanse we know today, allowing light to travel freely across space for the first time. We're literally seeing the aftermath of that transformation every time we look at the night sky, the reason distant starlight can reach us at all. Now, the James Webb Space Telescope is hunting for these elusive first stars, probing the deepest recesses of time. Its infrared eyes can detect the faint glow of their ancient light, stretched by cosmic expansion into wavelengths invisible to other telescopes. Early observations have revealed galaxies far older and more developed than expected, suggesting that star formation in the universe's infancy might have been even more vigorous than models predicted. Some theories propose that clusters of population Roman III stars could explain these unexpectedly bright early galaxies. their collective brilliance visible across billions of light years. Yet for all their significance, population Roman 3 stars remain ghostly figures in our cosmic history. No telescope has directly captured one, yet their fleeting lives ended long before Earth formed. But their legacy is everywhere. The heavy elements forged in their cores and scattered by their deaths became the building blocks for future stars, planets, and ultimately, life itself. Every atom of carbon in your body, every speck of iron in your blood, was once part of this first generation of stars. What's even more remarkable is how these stellar pioneers shaped the universe's large-scale structure. Their explosive deaths triggered shock waves that compressed nearby gas, accelerating the formation of new stars and the earliest galaxies. In this way, those first flickers of light didn't just illuminate the cosmos, they set in motion the intricate dance of galaxy assembly that would follow. And as we'll see next, that process of gas collapsing, stars igniting, and galaxies merging would eventually give rise to the cosmic web we inhabit today. Galaxies didn't emerge fully formed from the cosmic dawn. They were built piece by piece, like cities rising from the chaos of primordial rubble. Picture the early universe as a swirling construction site, where smaller clumps of stars and gas, drawn together by dark matter's invisible scaffolding, collided and merged in a slow-motion ballet. These violent encounters weren't just random crashes. They followed the hidden blueprint laid down by the cosmic microwave background's density fluctuations, with galaxies growing like beads on a string along the filaments of the cosmic web. The diversity of galaxies we see today, spirals with their graceful arms, ellipticals resembling glowing orbs, and irregulars twisting like cosmic splatters, tells the story of their turbulent upbringing. Spiral galaxies, like our Milky Way, are the result of relatively orderly mergers, where gas-rich collisions triggered waves of star formation that settled into rotating disks. Ellipticals, on the other hand, are the bruisers of the cosmos, forged in catastrophic collisions so violent they erased all traces of structure, leaving behind smooth, featureless giants. And irregulars, they're the misfits, often shaped by near misses or gravitational harassment from larger neighbors, their stars strewn like scattered paint. But galaxies aren't just shaped by gravity's tug of war. At the heart of nearly every large galaxy lurks a supermassive black hole, some weighing billions of times the sun's mass. These cosmic monsters aren't passive occupants, they're active players, regulating star formation with ferocious energy. When a black hole feeds on surrounding gas, it can unleash jets of plasma moving at nearly the speed of light, heating up the galaxy's gas reservoirs and stifling the birth of new stars. It's a cosmic feedback loop. Too much star formation fuels the black hole, which then quenches further star formation, maintaining a delicate balance. Without these black hole thermostats, galaxies might have burned through their gas too quickly, leaving the universe devoid of the long-lived stars that make life possible. The cosmic web itself is a testament to the enduring influence of those primordial density variations. Galaxies aren't scattered randomly, they cluster along vast, intersecting filaments, with colossal voids stretching between them like bubbles in foam. This structure mirrors the faint ripples in the CMB, magnified over billions of years by gravity's unrelenting pull. Supercomputer simulations recreate this growth with stunning accuracy, showing how dark matter's gravitational wells funneled gas into the web's intersections, creating the seeds of galaxy clusters. Yet the story isn't over. Even now, galaxies continue to evolve. The Milky Way and Andromeda are on a collision course, set to merge in about 4 billion years, a fate shared by countless other galaxies across the cosmos. With each collision, new stars are born, black holes awaken, and galactic structures transform. It's a reminder that the universe is anything but static. The same primordial energy that sparked the first galaxies still drives their evolution today, weaving an ever-changing tapestry of light and matter across the cosmic expanse. And as we'll see next, that energy doesn't just shape galaxies, it holds the key to the universe's ultimate fate. The universe's fate hinges on a cosmic tug of war between two invisible titans, dark energy, relentlessly pushing space apart, and gravity, struggling to pull it back together. Right now, dark energy is winning, accelerating the expansion faster than astronomers predicted just a few decades ago. But how this battle plays out over trillions of years depends on secrets hidden in the cosmic microwave background. That ancient light doesn't just tell us where we've been, it's a crystal ball revealing where we're headed. One possibility is the Big Freeze, a slow, quiet end where expansion stretches space so thin that galaxies vanish beyond the horizon of visibility, stars burn out, and the universe fades into an eternal, frozen darkness. Alternatively, gravity could stage a comeback if dark energy weakens over time, pulling everything back in a cataclysmic Big Crunch, a mirror image of the Big Bang where the universe collapses into a searing singularity. Or there's the more dramatic Big Rip, where dark energy grows stronger, eventually overpowering not just galaxies but atoms themselves, tearing reality apart at the seams. The CMB helps us weigh these scenarios like a cosmic scale, by measuring the universe's geometry, whether space is flat, positively curved like a sphere, or negatively curved like a saddle. Scientists can determine which fate is most likely. Planck's precision data shows space is flat to within a razor-thin margin, suggesting the universe will expand forever, growing colder and emptier. But geometry isn't the only clue. The CMB's fluctuations also reveal how much dark energy exists and whether its strength changes over time. Right now, it appears constant, pointing toward that endless expansion. Yet if future observations find it fluctuating, all bets are off. What's fascinating is how these grand cosmic destinies trace back to the universe's first moments. Those quantum fluctuations imprinted on the CMB didn't just shape galaxies, they set the initial conditions for everything that followed, like a domino chain 14 billion years long. The same primordial energy that ignited inflation may still be at work today, disguised as dark energy. If so, the universe's birth and death are bookends of the same story, written in the language of that faint afterglow. But the most humbling thought, we're living in the universe's golden hour, a brief window where the cosmos is neither too young nor too old to support life. A trillion years from now, the CMB will have faded into near nothingness, and any civilizations born then might never know the universe had a beginning at all. That makes our ability to decode these whispers from the dawn of time not just a scientific triumph, but a fleeting cosmic privilege. Now, to truly grasp how the CMB reveals the universe's geometry, we need to think like surveyors mapping an unimaginably vast landscape. Those subtle temperature variations aren't just thermal fingerprints, they're the universe's way of showing us the curvature of space itself. If the cosmos were positively curved, like the surface of a balloon, distant light beams would converge, making hot and cold spots appear larger. A negatively curved universe would stretch them smaller, but the CMB's patterns match neither extreme, they're just right for a flat universe, one where parallel laser beams shot across the void would never meet. This flatness isn't an accident. It's a direct consequence of inflation, which stretched space so violently that any primordial curvature became undetectable, like flattening a crinkled sheet by pulling its edges. The CMB's geometry also confirms a staggering truth. The universe's total energy density, the combined mass of matter, and dark energy is perfectly balanced to maintain this flatness. Too much and space would curve inward, too little and it would sag. That we exist in this precise equilibrium is either a cosmic coincidence or a clue to deeper laws we've yet to uncover. Yet, even as the CMB paints this picture, it leaves mysteries unresolved. Why does dark energy have the exact strength needed to make the universe flat? Is its constancy an illusion that will shatter with future observations? And if the cosmos is truly infinite, what does that mean for the nature of reality? The answers may lie in the next generation of experiments, probing the CMB's polarization for whispers of gravitational waves, or hunting for anomalies that could rewrite our cosmic story. One thing's certain, the universe's fate isn't just written in the stars, it's encoded in the oldest light there is. The shape of the universe isn't just an abstract curiosity. It determines everything from how light travels across space to the ultimate fate of all existence. Thanks to the cosmic microwave background, we can measure this geometry with astonishing precision. Picture space as an enormous sheet of paper. If the universe were positively curved like a sphere, parallel lines would eventually converge. A negatively curved universe shaped like a saddle would make them diverge, but the CMB's temperature fluctuations reveal something extraordinary. Our cosmos is flat too, within a margin of error of just 0.4%, meaning those lines stay perfectly parallel forever. This flatness isn't a lucky coincidence, it's a smoking gun for cosmic inflation. When the universe underwent its explosive expansion in the first fraction of a second, any initial curvature would have been stretched so dramatically that space became effectively flat. Just like blowing up a balloon to cosmic proportions makes its surface appear locally flat. The CMB's patterns act as a cosmic spirit level, confirming this prediction with razor-sharp accuracy. Those tiny hot and cold spots have precisely the angular size expected in a flat universe, a match so exact it would be like tossing a coin 1 billion times and getting heads exactly 500 million times. But flat geometry has mind-bending implications. It suggests the universe could be infinite, stretching forever without boundary or edge. Even more intriguing is what flatness tells us about the universe's energy budget. For space to lack intrinsic curvature, the total density of matter, and dark energy must be perfectly balanced at what cosmologists call the critical density. Imagine this as a cosmic tipping point. Too much mass and gravity would curve space inward, too little and it would sag outward. The fact we're perched precisely on this knife edge hints at deep connections between inflation, dark energy, and the fundamental laws of physics we're still unraveling. Had the CMB revealed even slight curvature, our understanding of cosmology would be radically different. A closed universe might have eventually collapsed in a big crunch, while an open one could have stretched into infinite cold emptiness far sooner. Instead, flat geometry supports the current leading scenario, an eternal expansion where galaxies eventually vanish beyond an unreachable horizon, leaving isolated islands of stars drifting in ever-growing darkness. Yet mysteries remain. Why does the universe's energy density balance so perfectly? Is this fine-tuning a clue to deeper physics? Or could multiple universes with different geometries exist beyond our observable horizon? The next frontier lies in the CMB's polarization, a subtler fingerprint that could reveal even more about the universe's shape and origins. When light scatters off electrons in the early universe, it becomes polarized, carrying information about the last time those photons interacted with matter. This polarization has two distinct patterns: E modes, created by density fluctuations, and the far fainter B modes, which could carry the imprint of primordial gravitational waves from inflation. Detecting these B modes would be like finding the brushstrokes of the universe's first moments. potentially confirming not just inflation's role, but whether space-time itself was quantumly wrinkled at the smallest scales. Experiments like the Simons Observatory and future space missions are hunting for these elusive signals. If successful, they might answer whether our flat universe is just one bubble in a vast multiverse, each with its own geometry and physical laws. The CMB has already rewritten our cosmic story once. As we probe deeper into its polarized whispers, the next chapter could redefine our place in the grand tapestry of reality. Light doesn't just carry brightness, it holds secrets in its twist and sway. The cosmic microwave background's polarization is like finding hidden writing in the glow of a candle, subtle imprints left by the last time those ancient photons brushed against electrons in the primordial plasma. When light scatters, it doesn't just bounce, it organizes, leaving behind faint patterns that cosmologists decode like cosmic hieroglyphs. The most common of these, E-modes, are the universe's fingerprint, showing where matter clumped and stretched under gravity's pull. But it's the rarer B-modes that have scientists holding their breath. These twisted, swirling patterns could be the telltale sign of primordial gravitational waves, ripples in space-time itself, frozen in the instant of inflation's furious expansion. Think of it this way: if the CMB's temperature map is a photograph of the infant universe, its polarization is the audio recording capturing not just how things looked, but how they moved. Detecting B-modes would be like hearing the echo of the Big Bang's first shudder, a direct snapshot of space-time vibrating as the universe ballooned from smaller than an atom to cosmic proportions in less than a blink. The challenge: these signals are absurdly faint, buried under interference from galactic dust and the swirl of magnetic fields. Experiments like BICEP, nestled in the pristine darkness of the South Pole, and the Simons Array, with its army of ultra-sensitive detectors, are racing to tease out this whisper-thin signal from the noise. What makes this hunt so thrilling is the stakes. If B-modes are found, they'd confirm inflation beyond doubt, locking in our understanding of the universe's explosive first moments. The strength of these waves would even reveal inflation's energy scale, telling us whether it was a gentle swell or a catastrophic quake. But there's a twist. Some theories predict B-modes so weak they might forever elude detection, while others suggest alternative origins, like cosmic strings, hypothetical defects in space-time left over from the early universe. Every new polarization map is a high-stakes treasure hunt where the prize could rewrite physics textbooks. Yet polarization isn't just about the past. It's a lens into the universe's entire history. As CMB photons traveled for billions of years, their polarization was subtly distorted by galaxies and dark matter, a phenomenon called gravitational lensing. By mapping these distortions, scientists can trace the invisible scaffolding of dark matter woven through the cosmos, even reconstructing how structures grew over time. It's like reading the universe's diary, each page written in the bend and warp of ancient light. But just when we think we've cracked the code, the CMB throws a curveball. Strange asymmetries, unexpected cold spots, and puzzling alignments, collectively dubbed the axis of evil, defy standard predictions. Some argue these are mere statistical flukes, while others whisper about entirely new physics. Could they hint at a pre-Big Bang era, or even a sibling universe brushing against ours? The answers might lie in the next generation of experiments, probing polarization with ever greater precision. One thing's certain: the universe's oldest light still has stories left to tell, and we're only beginning to listen. The cosmic microwave background is the most precise snapshot we have of the early universe, but it's not flawless. Scattered across that near-perfect glow are strange blemishes, anomalies that defy our best cosmological models. Take the infamous cold spot, a region in the southern sky significantly cooler than its surroundings. Under standard physics, such a feature should appear only once in every 1,000 simulated universes. Yet there it sits, a cosmic bruise spanning nearly 1 billion light-years, as if something vast and unseen left its mark on the fabric of space-time. One tantalizing explanation: the cold spot could be a collision scar from a parallel universe. In certain multiverse theories, our cosmos isn't alone but one bubble in an endless froth of universes, each with its own physical laws. If another bubble brushed against ours during inflation, the energy released might have left a shadow in the CMB. It's a radical idea, but not pure speculation. The math checks out. Alternatively, the cold spot might trace its origins to a supervoid, an enormous region of space nearly empty of galaxies, where light loses energy climbing out of its gravitational well. Yet surveys find no void large enough to explain the temperature drop, deepening the mystery. Then there's the hemispheric asymmetry, a baffling lopsidedness in the CMB's temperature fluctuations. One half of the sky shows stronger variations than the other, as if the universe forgot to smooth itself evenly. This isn't just a statistical quirk, it violates the cosmological principle, the bedrock assumption that the universe should look roughly the same in all directions. Some theorists propose this tilt stems from primordial gravitational waves distorting space-time before inflation ended. Others suggest it's a relic of quantum entanglement between our universe and another, freezing into the CMB like a fingerprint. But before we rewrite physics, there's a humbler possibility. These anomalies might be measurement errors or artifacts of how we process CMB data. Dust in our own galaxy, subtle instrument biases, or even the way we project a spherical sky onto flat maps could introduce false asymmetries. The Planck satellite team ran exhaustive checks, and the anomalies persisted, but with margins of error slim enough to keep skeptics questioning. What's undeniable is that these puzzles push cosmology forward. Future observatories, like the proposed CMB-S4 project with its army of ground-based telescopes, will map the CMB's polarization with unprecedented precision. Either they'll confirm these anomalies as real, forcing us to rethink inflation, dark energy, or even the multiverse, or they'll reveal them as mirages, proving once again how easily our tools can deceive us. Either outcome is thrilling, because the greatest lesson of the CMB isn't just what it reveals, but what it whispers we've yet to understand. The universe, it seems, still holds cards close to its chest. And if these anomalies are real, they might be our first glimpse beyond the horizon of our observable universe, hints of a reality vaster and stranger than we dared imagine. Which brings us to one of cosmology's most provocative ideas, that the CMB's fingerprints don't just trace one universe, but many. The idea that our universe might be just one bubble in an endless cosmic froth is as exhilarating as it is humbling. Inflationary theory doesn't just explain the smoothness of our cosmos, it hints at something far grander. If space-time expanded like a rapidly inflating balloon in those first moments, why couldn't other regions have ballooned into entirely separate universes, each with its own unique physics? Picture a cosmic kaleidoscope, where every twist creates a new reality with different constants, some where gravity is stronger, others where atoms never form, and perhaps a rare few where conditions are just right for life like ours. This multiverse hypothesis isn't pure fantasy. It's grounded in the math of quantum fluctuations and string theory. When inflation stretched those microscopic quantum ripples to cosmic scales, it might have also spawned pocket universes beyond our observable horizon. The cosmic microwave background could hold clues. Some theorists suggest that unusual patterns, like the cold spot or hemispheric asymmetry, might be bruises from collisions with neighboring universes, like fingerprints pressed against the fabric of our reality. No smoking gun exists yet, but the search is on. Future CMB experiments might detect telltale circular patterns in polarization maps, cosmic crash sites where another universe nudged ours long ago. What makes this idea so compelling is how it tackles the fine-tuning problem. Our universe's constants, the strength of gravity, the mass of electrons, are exquisitely balanced for life. Tweak them slightly and stars wouldn't ignite or atoms would fly apart. The multiverse offers an elegant explanation. With infinite universes, some are bound to hit the jackpot by sheer chance. We just happen to live in one where the numbers lined up. It's like finding a single perfectly tuned radio station in a sea of static. The odds seem impossible until you realize there are countless radios. Yet the multiverse remains controversial. Without a way to observe these other realms directly, some argue it's more philosophy than science, but that hasn't stopped physicists from devising ingenious tests. If another universe grazed ours, it might have left gravitational waves imprinted in the CMB's B-mode polarization, a fingerprint we could uncover with next-generation telescopes. Others propose that dark energy's mysterious strength could be a side effect of neighboring universes tugging on ours through higher dimensions. Whether the multiverse is real or not, it reshapes how we see our place in existence. We might be one tiny spark in an infinite cosmic tapestry, or we might be alone in a singular, finely tuned universe. Both possibilities are equally awe-inspiring. And as we push the boundaries of cosmology, we're not just mapping galaxies, we're probing the very nature of reality itself. Now consider this: if life emerged in our universe because the constants aligned just right, could the same happen elsewhere? The echoes of primordial energy didn't just shape galaxies, they set the stage for chemistry, for planets, for the delicate conditions that allow life to arise. From the quantum ripples of inflation to the vast cosmic web, every step in the universe's evolution was a roll of the dice. Yet here we are, a product of those ancient fluctuations, gazing up at the stars and wondering if we're alone. The search for extraterrestrial life isn't just about telescopes and radio signals. It's about understanding how the universe's first whispers made biology possible at all. Those subtle ripples in the cosmic microwave background did far more than sculpt galaxies. They wrote the recipe for life itself. Imagine if those primordial density variations had been just slightly smoother. Matter would have spread too evenly across space, never clumping enough to ignite stars or forge planets. No swirling spiral arms cradling solar systems. No rocky worlds orbiting at just the right distance for liquid water. The universe would be a featureless void, its hydrogen gas forever drifting in darkness. But gravity had something to work with, thanks to those microscopic quantum fluctuations stretched to cosmic scales during inflation. Slightly denser regions pulled in more matter, growing over billions of years into the galaxies we see today. Within those galaxies, generations of stars lived and died, forging heavier elements in their cores and scattering them across space in supernova explosions. Carbon, oxygen, iron, the very atoms that make up our bodies were forged in those stellar furnaces, then recycled into new stars and planets. The Goldilocks conditions for life didn't just happen by chance. They were set in motion by imperfections in the universe's first light. Even the expansion rate of the cosmos plays a starring role in this story. If dark energy had been stronger, space would have torn apart before galaxies could form. Too weak, and gravity might have collapsed everything back into a fiery crunch long before life could emerge. It's as if the universe walked a tightrope, balancing its ingredients with precision to allow complexity to flourish. And the evidence is written in the CMB's temperature mapper, a blueprint showing just how finely tuned those initial conditions had to be. This cosmic connection isn't just theoretical. Look at Earth's position in the Milky Way, far enough from the chaotic galactic center to avoid lethal radiation, yet close enough to generations of earlier stars to inherit their heavy elements. Or consider Jupiter's role as a gravitational shield, deflecting asteroids that might otherwise bombard our planet. These aren't isolated accidents. They're downstream consequences of those primordial ripples, cascading through billions of years of cosmic evolution. What's astonishing is how fragile this chain of events appears. Alter the CMB's fluctuations by even a fraction, and the universe might never have built the complex structures that make life possible. It raises profound questions. Are we the lucky winners of a cosmic lottery? Or is there some deeper principle that favors life's emergence? And if other universes exist with different initial conditions, how many of them could support beings gazing up at their own night skies? The answers may lie in the next generation of experiments designed to probe the CMB with unprecedented precision. From space-based observatories to groundbreaking telescopes, scientists are preparing to decode even fainter whispers from the universe's infancy, clues that could reveal whether life is a rare accident or an inevitable consequence of cosmic design. The next leap in our cosmic detective story is already taking shape, with groundbreaking missions poised to peel back even more layers of the cosmic microwave background's secrets. Projects like CMB S4, a network of ultra-sensitive telescopes in Chile and Antarctica, and Japan's LightBird satellite are gearing up to scan the sky with resolution so sharp they could spot primordial gravitational waves buried in the CMB's polarization like whispers in a hurricane. These aren't just incremental upgrades, they're quantum leaps in precision, designed to measure temperature variations down to millionths of a degree and polarization patterns finer than the weave of a spider's web. What makes these missions revolutionary is their teamwork. Ground-based telescopes like CMB S4 benefit from stable, high-altitude sites where Earth's atmosphere is thin and dry, critical for reducing interference when hunting microwave signals. But space-based observatories like LightBird have an even clearer advantage: no atmosphere at all. Orbiting beyond Earth's turbulent air, they'll capture the CMB's faintest signals without distortion, like reading a book without smudged glasses. Together, these efforts form a tag-team approach, cross-verifying findings to weed out false positives and zero in on genuine cosmic clues. The stakes couldn't be higher. If these missions detect the telltale curl of B-mode polarization from primordial gravitational waves, it would confirm inflation's wildest predictions, locking in our understanding of the universe's explosive first moments. But there's room for surprises too. Unexplained anomalies in the data might hint at entirely new physics particles beyond the standard model, extra dimensions, or even evidence of a cyclic universe bouncing through endless cycles of expansion and contraction. The CMB isn't just a relic, it's a frontier where known physics meets the unknown, and every new measurement could rewrite the rules. For amateur astronomers, this golden age of cosmology isn't just a spectator sport. While you won't spot the CMB with a backyard telescope, citizen science projects like Planck's Legacy Archive let anyone scour satellite data for cosmic oddities. Universities often crowdsource help classifying galaxy clusters or tracking interstellar dust that could obscure CMB signals. And with open-source software like HealPix, even hobbyists can visualize the universe's baby pictures, exploring temperature maps that researchers used just decades ago. The thrill: you might notice something professionals missed, like the amateur who spotted a strange, cold ring in Planck data that later sparked a scientific paper. This is the beauty of the CMB's legacy. It's not just a snapshot frozen in time. It's a living puzzle inviting everyone, from Nobel laureates to curious stargazers, to piece together the story of our cosmic origins. As these next-generation missions come online, they won't just refine our models. They'll remind us that the universe's greatest mysteries are still within reach, written in light that's been traveling since the dawn of time. You don't need a PhD or a $1 million telescope to explore the cosmic microwave background. Some of the most exciting discoveries start with ordinary people gazing at extraordinary data. Projects like Galaxies have revolutionized how we study the universe by inviting volunteers worldwide to classify galaxies in telescope images, tasks where human intuition often outperforms algorithms. But the CMB's reach goes even further. Amateur radio astronomers have successfully detected its faint whisper using modified satellite dishes and homemade receivers, proving you don't need a budget to touch the edge of space and time. Take the story of a retired electrical engineer in Minnesota who built a backyard radio telescope from salvaged parts. By patiently filtering out terrestrial interference, he captured the CMB's characteristic signal, a feat that would have been science fiction just decades ago. Or consider the high school teacher whose students analyzed public data from the Planck satellite, spotting subtle anomalies that sparked new academic papers. These aren't isolated cases. They're part of a growing movement where cosmic exploration isn't confined to elite institutions but flourishes in garages, classrooms, and living rooms. This democratization of cosmology does more than advance science. It reshapes how we relate to the universe. When someone traces the CMB static on their laptop screen or identifies a galaxy cluster in a crowdsourced project, they're not just observing history, they're participating in it. The awe of realizing that faint signal traveled 14 billion years to reach us bridges the gap between abstract theory and visceral wonder. Online forums buzz with amateur cosmologists debating polarization patterns or collaborating to map local radio interference that could mask primordial signals. Educational initiatives amplify this connection. Museums now host CMB visualization workshops where visitors can hear the universe's oldest light translated into sound, a deep, haunting hum that makes cosmic expansion tangible. Apps like Space Audio Labs let users explore frequency variations across the sky, turning raw data into an immersive experience. Even video games incorporate real CMB datasets, allowing players to navigate the early universe while learning how density fluctuations seeded galactic structures. The beauty of this public engagement lies in its reciprocity. While professionals provide the tools and data, citizen scientists contribute fresh perspectives. A graphic designer might notice an unusual pattern in a temperature map that theorists overlook, or a musician might detect rhythmic anomalies in the CMB's frequency spectrum. These collaborations remind us that unraveling the universe's mysteries isn't just about advanced math. It's about human curiosity in all its forms. As we prepare to tackle Big Bang myths head-on, remember this: the CMB isn't locked away in an ivory tower. It's a living, breathing frontier where anyone with passion can contribute to the greatest story ever told, the story of where we all came from, written in light older than stars themselves. One of the most persistent myths about the Big Bang is that it was some kind of fiery detonation in empty space, a cosmic bomb going off at a single point. But here's the truth: the Big Bang didn't happen somewhere in the universe. It was the universe. Space, time, and matter all burst into existence together, unfolding from an unimaginably hot, dense state. Picture stretching a rubber sheet in every direction at once. That's closer to what cosmic expansion really looks like. There's no center, no edge, just space itself growing and carrying galaxies along for the ride. This misunderstanding leads to another common mix-up: the idea that the cosmic microwave background marks some distant boundary, like a glowing shell at the edge of the cosmos. In reality, the CMB is all around us, a bath of ancient light filling every cubic inch of space. We're not looking out to see it, we're looking back, peering through layers of time in every direction. The reason it appears as a sphere isn't because we're at the center, but because we're embedded in the same expanding fabric as everything else. Imagine standing in a dense fog. No matter which way you turn, the mist appears at the same distance, not because you're in the middle of it, but because you're surrounded by it. The CMB works the same way a relic glow from when the universe became transparent, now stretched and cooled by billions of years of expansion. These misconceptions often arise from trying to fit cosmic scales into everyday intuition. We're used to explosions having a center and edges, but the universe operates by different rules. The CMB's uniformity is actually proof there's no special location. Every observer, no matter where they are in the cosmos, would see the same glow surrounding them. It's a cosmic democracy where no spot is privileged over another. Now, here's where things get even stranger. The CMB isn't just a fossil. It's a bridge between the largest scales of the cosmos and the tiniest quirks of quantum mechanics. Those faint temperature variations we see, they're thought to be magnified quantum fluctuations, tiny, random ripples in energy that existed when the universe was smaller than an atom. During inflation, these microscopic wrinkles were stretched to cosmic proportions, becoming the seeds for galaxies and galaxy clusters. In a very real sense, the vast structures we see today trace back to quantum jitters frozen into the fabric of space-time itself. This connection between the quantum and cosmic realms is one of the most profound insights of modern physics. It suggests that the universe's grand architecture owes its existence to the same unpredictable behaviors that govern particles in a lab. The next time you look up at the night sky, remember, the stars and galaxies aren't just distant objects, they're the grown-up versions of quantum whispers, echoes of the universe's first moments written in light. At the heart of the cosmic microwave background story lies one of the most astonishing connections in all of science, the invisible thread tying together the frenzied quantum world of the ultra-tiny with the vast cosmic structures we see today. Those delicate density variations in the CMB, the ones that seeded all galaxies and stars, didn't arise from some primordial chaos. They were born from quantum mechanics itself, from the same unpredictable flickering of energy that governs subatomic particles. In those first fractions of a second after the Big Bang, when the entire observable universe was compressed into a space smaller than an atom, quantum fluctuations caused microscopic ripples in the fabric of reality. Then inflation struck, stretching those subatomic wrinkles to cosmic proportions in less time than it takes light to cross a single proton. This cosmic magnification turned quantum noise into architecture. What began as random particle movements became hills and valleys in the early universe's density, slightly hotter spots where matter was more concentrated, cooler spots where it was more sparse. Over billions of years, gravity amplified these differences, sculpting them into the galaxies and voids we observe today. It's a staggering thought. The grand spiral of Andromeda and the vast emptiness between galaxy clusters might trace back to quantum jitters smaller than a trillionth of a centimeter. The implications shake the foundations of physics. Normally, quantum effects average out at larger scales. You don't see quantum uncertainty making planets wobble unpredictably. But the CMB shows quantum behavior writ large across the cosmos, frozen into the universe's structure during its inflationary growth spurt. This discovery has turned cosmology into a testing ground for theories aiming to bridge quantum mechanics and gravity, the holy grail of modern physics. Concepts like loop quantum gravity or string theory predict subtle signatures that might be encoded in the CMB's polarization patterns. future experiments could uncover evidence for extra dimensions or quantum foam, the idea that space-time itself might be pixelated at extremely small scales. Yet for all its explanatory power, this quantum-to-cosmic connection raises profound questions. Why did these particular fluctuations emerge from the quantum haze? Was there something special about their initial configuration, or is our universe just one random outcome among countless possibilities? Some theorists suggest we're seeing the first hints of a multiverse, an infinite froth of universes, each with its own unique quantum history. Others propose that deeper laws guided the fluctuations toward life-friendly patterns we now observe. What's undeniable is how this discovery has transformed our understanding of reality's architecture. The universe isn't just governed by quantum rules at small scales and cosmic rules at large ones. It's a seamless continuum where microscopic randomness blossoms into macroscopic order. The next time you gaze at the night sky, consider this: you're not just seeing stars, you're witnessing quantum mechanics painted across the cosmos, a masterpiece 14 billion years in the making. This revelation doesn't just belong to physicists, it reshapes how all of us perceive existence. If the universe's largest structures grew from quantum seeds, does that mean reality is fundamentally uncertain at its core? Or is there a hidden determinism we've yet to uncover? These aren't just technical questions about the early universe. They're philosophical inquiries about the nature of causality, randomness, and whether the cosmos could have turned out differently. The answers might lie in the next generation of CMB experiments, probing those frozen quantum whispers for clues about reality's deepest workings. The cosmic microwave background doesn't just illuminate the universe's physical origins, it casts light on existential riddles that have haunted humanity for millennia. Why does anything exist at all? The staggering precision of those primordial density fluctuations, the delicate balance of dark energy and gravity, the improbable conditions that allowed galaxies and eventually life to emerge, all point to a cosmos that seems almost designed for complexity. Yet design implies a designer, and here science treads cautiously. Some physicists argue the fine-tuning is statistical inevitability in a multiverse, where countless universes bubble into existence with random parameters, and we simply inhabit the rare one where the numbers lined up. Others propose deeper, undiscovered laws that constrain the universe's initial conditions, making life-friendly outcomes unavoidable. This debate echoes far beyond laboratories. Philosophers have wrestled with the why something rather than nothing question since antiquity, from Leibniz's metaphysical principles to Heidegger's ponderings on being. The CMB injects hard data into these abstract discussions, transforming age-old speculation into testable hypotheses. Those faint temperature variations aren't just data points, they're cosmic breadcrumbs leading toward answers about causality itself. Did time have a true beginning, or is the Big Bang merely a phase in an eternal cycle? The CMB's flat geometry and uniformity suggest a definitive start, but alternative models like bouncing cosmologies propose an endless loop of expansion and contraction, where each Big Bang springs from a previous universe's collapse. What's striking is how these scientific theories resonate with ancient creation myths. Hindu cosmology speaks of universes breathing in and out over eons, while modern physics calculates cyclic models with mathematical rigor. The CMB becomes a Rosetta Stone, translating between empirical observation and humanity's timeless hunger for origin stories. Artists and writers have seized on this duality, using the afterglow as a metaphor for existential wonder. Composer John Adams's Dr. Atomic opera incorporates actual CMB frequency data into its score, while visual artists like Katie Patterson create installations translating cosmic microwave patterns into sound and light, making the abstract palpably emotional. This cultural ripple effect reveals something profound. The CMB isn't merely an artifact of astrophysics. It's a mirror reflecting our collective awe at existence. Whether through equations or poetry, humanity grapples with the same core mystery that 14 billion years ago, quantum randomness conspired with physical laws to create a universe capable of contemplating itself. The afterglow's whispers remind us that science and art are twin responses to the sublime, one measuring the wavelengths of creation, the other giving voice to the wonder it inspires. Now consider how this primordial light has permeated popular imagination. From films like Melancholia, using CMB visuals to symbolize cosmic interconnectedness, to novels like The Three-Body Problem, weaving its fluctuations into alien communication, the afterglow has become a cultural touchstone for humanity's place in the vastness. Musicians sample its static as ambient soundscapes, while digital artists remix Planck satellite data into immersive experiences. This creative engagement isn't incidental, it's proof that the universe's oldest light still sparks new ways of seeing, blending empirical discovery with mythic resonance. The CMB bridges lab and gallery, offering both the precision of science and the ambiguity that fuels art's deepest inquiries. As we'll see next, this interplay between cosmic discovery and cultural expression isn't just ornamentation. It's how humanity metabolizes the universe's grand narratives, turning data into meaning. The afterglow's journey from scientific anomaly to artistic muse reveals a truth as profound as the physics itself. We're not just observers of the cosmos, but storytellers weaving its echoes into the fabric of human experience. The cosmic microwave background isn't just data, it's a muse. Composers have transformed its faint static into symphonies, translating temperature fluctuations into haunting musical notes that echo the universe's infancy. In John Luther Adams' Become Ocean, the CMB's subtle variations become swelling orchestral textures, mirroring the primordial sea of particles from which all matter emerged. Meanwhile, electronic musicians like Jean Mitchell-Jarre have sampled actual Planck satellite data, weaving the universe's oldest light into ambient soundscapes where science and art blur into one. These creations aren't mere novelty, they're emotional portals, letting listeners feel the cosmos scale in ways equations alone cannot convey. Visual artists have been equally captivated. Team Lab's immersive installations envelop viewers in dynamic projections of CMB maps, where warmer regions glow amber and cooler ones shimmer in cobalt, turning abstract cosmology into visceral experience. At the Hayden Planetarium, visitors lean back under domes animated with the afterglow's patterns, watching as quantum ripples evolve into galaxies, a time lapse of creation rendered in light. Even textile artists like Leah Cook have woven CMB temperature data into tapestries, their threads tracing the exact contours of primordial density variations. The result, a tangible connection between human craftsmanship and cosmic architecture, reminding us that the same fluctuations guiding stars also inspire hands at looms. This cultural resonance speaks to something deeper than aesthetics. The CMB's patterns, random yet structured, mathematical yet sublime, tap into a universal human yearning to find meaning in the vastness. Filmmakers leverage this power repeatedly. In Tree of Life, Terrence Malick juxtaposes CMB visuals with intimate human drama, framing existence as a continuum from quantum flickers to personal memories. Video games like No Man's Sky use procedural generation algorithms inspired by inflationary models, their infinite worlds echoing the universe's own fractal beginnings. Even fashion designers like Iris Van Herpen have draped models in dresses patterned after CMB polarization maps, their intricate pleats mirroring the twist of ancient photons. What unites these works is their ability to democratize cosmic wonder. You don't need a physics degree to stand awestruck before a CMB-inspired sculpture or feel your heartbeat sync with a sonification of its data. By transmuting raw science into sensory experience, artists give the public new language for engaging with profound ideas. A child hearing the afterglow's frequencies might grasp deep time intuitively, while a gallery-goer tracing a CMB mural with their fingers connects personally to the universe's scaffolding. This synergy between labs and studios is transformative. It turns passive observation into participatory awe. Yet the CMB's cultural footprint extends beyond galleries and concert halls. It's reshaped spiritual dialogue too. Tibetan monks have incorporated its imagery into mandalas, seeing parallels between cosmic cycles and Buddhist concepts of impermanence. Christian theologians ponder whether the afterglow's uniformity reflects a creation ex nihilo, while indigenous storytellers draw links between its ripples and ancestral tales of world-making. These interpretations aren't at odds with science. They're complementary narratives, each grappling with the same existential marvel, that we're here at all, born from whispers of energy older than stars. The afterglow's journey from scientific dataset to cultural icon reveals a truth often overlooked. Understanding the cosmos isn't just about collecting facts. It's about integrating those truths into the human story, letting them resonate in music, dance, and shared wonder. When a poet compares the CMB's static to a lullaby sung by the universe to itself, or a VR artist lets you step inside its fluctuations, they're not just explaining cosmology, they're expanding how we belong to it. And that's the afterglow's greatest gift. It doesn't just show us where we came from. It invites us to see ourselves as active participants in an unfolding cosmic epic, still shaped by the same primordial energies that lit the dark 14 billion years ago. The cosmic microwave background is more than a relic. It's a living chronicle, a story still being written across the canvas of space and time. Every photon in that ancient glow carries layers of meaning, from the quantum tremors of the universe's first moments to the gravitational echoes of galaxy clusters forming billions of years later. It's astonishing to realize that the same light breaking free from primordial plasma now lands in telescopes as faint static, whispering secrets about dark energy's push and dark matter's pull. This isn't just astronomy, it's cosmic archaeology where we piece together the universe's history from fragments of heat left behind. What makes the CMB truly extraordinary is its duality. It's both a snapshot and a prophecy. The temperature variations tell us where matter clumped in the past, but they also encode the universe's destiny. Those subtle ripples set the stage for everything: the spin of spiral galaxies, the vast voids between superclusters, even the chemical elements that make up our bodies. The iron in your blood, the calcium in your bones, they were forged in stars that formed because gravity had something to work with, thanks to those primordial imperfections. The universe's entire architecture, from the largest scales to the tiniest life-giving details, traces back to this afterglow, and the revelations aren't over. Next-generation telescopes like CMB S4 and LightBird are poised to peel back even deeper layers, hunting for the faint curl of B-mode polarization that could confirm inflation's wildest predictions. Imagine decoding gravitational waves from the universe's first trillionth of a second, or finding anomalies that hint at dimensions beyond our own. The CMB is like a palimpsest, a manuscript where older writing lingers beneath the surface, waiting to be uncovered. Every improvement in sensitivity, every new way of analyzing the data, could reveal text we didn't even know was there. This is why the cosmic microwave background captivates scientists and dreamers alike. It's not just about mapping the past, it's about glimpsing the future, Will dark energy tear the cosmos apart? Could alternate universes leave fingerprints in the polarization? The answers may already exist, hidden in patterns we haven't yet learned to read. The universe has been broadcasting its story since the beginning, and we're only now tuning in to the right frequency. So the next time you see static on an old television, take a second look. That snow isn't just noise, it's the afterglow of creation, a signal from the edge of time itself. And as we continue to listen, who knows what other chapters of the cosmic saga we'll uncover? The journey doesn't end here. Hit like if you're as awestruck by this as we are. Subscribe to join us for more deep dives into the universe's greatest mysteries, and drop a comment below. What cosmic question keeps you up at night? The cosmos is vast, but curiosity connects us all. Until next time, keep looking up.